Hey guys, in this lesson we would understand acid-base titrations. Titrations, as you have learned in previous grades, is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. The known solution, that is called the titrant, is added to the burette, and from the burette it is allowed to then flow into the analyte, that is the unknown solution in the titration flask. The reaction continues until the reaction is complete. So basically in burette we put a base, and in titration flask we put an acid. When a base is going to enter the acid, it is going to neutralize the acid. Into the acid is also added an indicator. That indicator is going to change color when acid and base are going to neutralize. When acid and base neutralize, or acid and base reaction has completed, or acid and base have reacted completely with each other, that point is called equivalence point. Whereas when the indicator is going to show a color change is called the endpoint. So that is where we stop the reaction. Now, acid-base titration is of three types. One is called strong acid, strong base titration, where both the acid and the base are strong acids and bases. Other is called weak acid, strong base titration. So in this type of titration, acid is weak and base is strong. And the last one is strong acid and weak base titration. In this lesson, we would discuss the calculation based on strong acid, strong base titration. Let's take an example for this. Let's say we have a 40 ml solution of 0.100 moles per liter HCl, that is acid, it's aqueous acid. This is being titrated with 0.1000 moles per liter NaOH aqueous. So we are given this is the volume of acid and acid is HCl. This is given to us as the concentration of acid is titrated with, we're given the concentration of base. Reaction is NaOH reacts with HCl to give NaCl, salt and water. This is also neutral and water is also neutral. That's why it's called a neutralization reaction. We have to calculate the pH of original solution of strong acid. So in the flask we have HCl. We have to find the pH of HCl. We know HCl is a strong acid. So strong acid is going to completely break down to give H positive and Cl negative. We know whenever we do the reaction, because it's aqueous, so this is basically dissolved in water. And when anything is dissolved in water, water is the one that is going to take up H positive ions or that is going to give off H positive ions depending upon if it is acting as an acid or base. Now here HCl is an acid, so HCl is going to give off H positive ions to H2O, will itself become Cl negative and will yield H3O positive ions. Now initially what has happened is that we have not added any base to this acid yet. Since no base has been added, so this acid has not yet been diluted with a base. Therefore the entire H3O positive ion is going to play a role in giving the pH of this strong acid. We know pH formula is negative logarithm of H3O positive ions. Now we want to find out the concentration of H3O positive ions. We are already given the concentration of HCl, and HCl is a strong acid, therefore it breaks down completely to give up H3O positive and Cl negative. So if we rewrite this equation, HCl reacts with water to give us Cl negative and H3O positive. You know the concentration of HCl is 0.100 moles per liter. This is going to completely give off 0.100 moles per liter of H3O positive ion concentration. Using this concentration, we can find out the pH. So pH is negative logarithm of 0.100, which would be equal to negative logarithm of 10 to the power minus 1. When we put this on the calculator, we'll be able to get pH as 1. So this is the pH of HCl before we add any NaOH from this burette to the titration flask. So right now it is just HCl present in the titration flask along with the indicator. Next part of the question wants us to calculate the pH of the solution before equivalence point after adding 20 milliliters of NaOH. Now HCl is not alone. in the titration flask, we have added 20 ml of NaOH in the flask as well. So when NaOH, that is 20 ml, this is the volume of NaOH, concentration of NaOH is given to us as 0.100 moles per liter. When this reacts with HCl that is already present in the flask, volume of this HCl is given to us as 40 ml, that is this, and concentration of HCl is known to us as also 0.100 moles per liter. When these two react, it is going to give us NaCl, that's an aqueous salt, and liquid water. So basically how this NaOH has split it up is, it has given off Na positive and OH negative. HCl splits up to give us H positive and Cl negative. OH negative and H positive is going to react together to form water, and Na positive and Cl negative will react together to give us NaCl. Now we would find out how many moles of OH negative have been released by NaOH and how many moles of H positive have been released by HCl in order to find out how many moles of water have been formed. For that, we would write down their breakdown reactions separately. Now NaOH, being a strong base, is going to completely break down to give us Na positive and OH negative ion. Now we're given the volume of NaOH to be 20 ml, that is equal to 0.020 liters. And we're given the concentration as 0.100 moles per liter. We know any balanced equation can be solved using stoichiometry or the number of moles. So we would calculate the number of moles using concentration and volume. As we know, number of moles is C times V, because concentration is number of moles divided by volume. Therefore, we would just multiply concentration and volume with each other. So we would get 0.100 times 0.020. That is equal to 0.002 moles. Now, since we see the reaction is balanced, 1 mole of NaOH gives us 1 mole of OH negative and 1 mole of Na positive ion. Therefore, 0.002 moles of NaOH will give us 0.002 moles of OH negative ion. Similarly, when we split up HCl in the presence of water, it will give us H3O positive ion and Cl negative ion. The concentration of HCl is also 0.100 moles per liter, and the volume of HCl is given to us as 40 ml, that is 0.040 liters. We use concentration and volume to get the number of moles of HCl present initially, and that would be equal to C times V, which is 0.100 times 0.040, and this would give us 0.004 moles. Hence, we can say initially, if HCl completely breaks to give us H3O positive ion, we would get 0.004 moles of H3O positive ions in the titration flask prior to adding any NaOH to it. So initially in the flask, we have only HCl that gives us H3O positive ions, which are equal to 0.004 moles. After adding NaOH, 0.002 moles of OH negative are released in the flask. Because of this, these 0.002 moles of OH negative and out of 0.004 moles of H3O positive, 0.002 moles of H3O positive will also react with the same number of moles of OH negative to form water, because H3O positive from HCl and OH negative from NaOH will now react to form water, and water is neutral. Since we have 0.004 moles of this and 0.002 moles of this, only 0.002 moles of H3O positive will react with 0.002 moles of OH negative to form 0.002 moles of water. That is shown by this step, and we are finally left with only 0.002 moles of H3O positive. So now in our titration flask, there are no longer 0.004 moles of hydronium ions. Instead, there are just 0.002 moles of hydronium ions left in the titration flask. So after adding 20 ml of NaOH or 0.002 moles of NaOH, we are left with hydronium ions equal to 0.002 moles in this titration flask. However, this titration flask now contains not just HCl but two solutions, It contains HCl and NaOH. HCl that it contains was what originally present, 40 ml, and NaOH is added to it, that is equal to 20 ml. So the total solution would be equal to 60 ml, which is 0.060 liters. Therefore, this flask is now containing these many moles of hydronium ions, and this is the volume of solution. We would use these moles and this volume to find out the concentration of this solution in the flask. We know concentration is number of moles divided by volume. Number of moles is 0.002 divided by 0.060, that is equal to 0.033 moles per liter. And this is the concentration of hydronium ions present in this flask. We would use this concentration to find out the pH of this flask at this time when 20 ml of NaOH has already been added to the flask. So pH is now going to use the concentration of H3O positive that we have calculated here, and that is equal to negative logarithm of 0.033, which is equal to 1.48. Therefore, pH at this point that we have got is 1.48. Next, they want us to calculate the pH at equivalence point, that is after adding 40 ml of NaOH. We can repeat the previous steps. We have NaOH volume now 40 ml, which is 0.040 liters. We have the same concentration as it was present originally, 0.100 moles per liter. This would give us Na positive and OH negative. So number of moles is concentration multiplied by volume, that would give us 0.004 moles. Now we have OH negative ions also equal to 0.004 moles. No change has happened to HCl. HCl gives us H3O positive ions and Cl negative ions. The HCl ions, the HCl moles that we had calculated earlier was already 0.004 moles. So H3O positive is still 0.004 moles. Now because this and this is going to neutralize, these are going to get subtracted with each other. So we would have H3O positive original minus OH negative moles, which is equal to 0.004 minus 0.004, that is equal to 0 moles. Hence, we are not left with any H3O positive moles inside the titration flask anymore. So this means no moles of H3O positive are left, as all the H3O positive ions have reacted with OH negative ions to give us liquid water. And we know concentration of water is 1 times 10 to the power of negative 7 moles per liter. Therefore, the pH is going to be equal to negative logarithm of 1 times 10 to the power negative 7, which when we put in the calculator will give us a pH of 7. This shows neutralization has happened, and this is called the equivalence point. So always remember, if we have equal number of moles of hydronium ions and hydroxide ions, they would neutralize each other to give us no moles left of any of these. Therefore, only water is present and the pH of water is 7. Now, if we are given a scenario where we have to calculate the pH of solution after equivalence point, that is after adding 50 ml of NaOH, then what is going to happen? We have NaOH that gives us Na positive and OH negative. NaOH concentration has not changed and it will not change as well because that's what has been given to us initially. So concentration is 0.100 moles per liter. Volume is now 50 ml added to the titration flask, which is 0.050 liters. So number of moles will be equal to concentration multiplied by volume, that is equal to 0.005 moles. Now we have hydroxide moles to be equal to 0.005. HCl has still not been added. It is whatever it was present originally. We have hydronium ions and Cl negative ions. Here the number of moles were 0.004. This is also 0.004 moles. Now we would see OH negative moles are more than hydronium ions moles. So we would subtract hydroxide ions and hydronium ions moles. Hydroxide ions are 0.005, hydronium ions are 0.004. That would give us 0.001. However, this is now hydroxide ions, not hydronium ions, because these are higher than this. So now in the titration flask, we have 0.001 moles of hydroxide ions. To find the pH, we know pH is pKw minus pOH. So it would be 14 minus pOH. So we would use these hydroxide ions to calculate the pOH and then subtract it from 14 to get the pH. However, to first change this to pOH, we need to find out the concentration of hydroxide ions. We just know the moles yet. We do not know the concentration yet. To find the concentration of hydroxide ions, we would need the number of moles of hydroxide ions and we would need the volume of solution in the flask. Number of moles of hydroxide ions are the ones that are left and have not been neutralized. So this is 0.001 and the volume of solution in the titration flask is now going to be equal to 40 ml HCl and 50 ml NaOH. That is equal to 90 ml of solution, which is 0.090 liters. So we would have the volume of solution to be 0.090 liters. That would give us 0.011 moles per liter concentration of OH negative ions in the titration flask. Therefore, pOH would be equal to negative logarithm of OH negative ions, that is negative logarithm of this concentration, and this gives us the pOH to be 1.95. However, the question wants us to find out pH, so that would be 14 minus pOH, which is equal to 14 minus 1.95, and that is equal to 12.05. Therefore, we notice that the pH has gone higher than 7, so this solution inside the titration flask is now basic solution because of higher concentration of NaOH as we have passed the equivalence point or the neutralization point. And this is how we calculate pH in a acid-base titration experiment at different times of addition of the base into the titration flask.